All right. So today we're going to continue on. Welcome back, everybody. Volleyballers, if you're watching this, hopefully you had a nice flight, and it is morning on November 19th, and you're watching it already in Anchorage in your study hall. I don't know. We'll see. Anywho, the bell ringer today is in your notes. Again, just stressing that. And this problem will relate back, so I just do it right underneath. But I want us to think about the following. And we're going to jump in here. We're going to find what was wrong before we do the bell ringer. Okay, if I try to do this, like we did the derivative and everything yesterday, I'm trying to find dH/dt, which I have that in my equation. Okay, so that's a good sign. We need to solve for this. When the depth is 8, so that's when the height here is 8, and we know that water is pumped in. Do I ever tell you anything about the radius in this problem? Nowhere in here do I mention a radius. Maybe not in words. Let me rephrase. It sounds like I'm trying to affirm what you just answered. Anywhere in our problem did we reference a radius ever, whether we explicitly stated it or not? In the drawing, do we have a radius given? We do, right? Now, unfortunately, any way do you guys know, or were we given dr dt, or how fast the radius is changing? So even if I tried to plug in here, we don't know what dH dt is because we're trying to find it, and I don't know what dr dt is, and I don't have a way to find it right now. We don't know the radius at any point. Like, there's issues here. We don't have anything to plug in for dr dt. We don't have anything to plug in for r because we're trying to find the radius here, and we don't have it yet. So there's issues about. Now, the good news is that when several of you talked about how easy geometry was, it's perfect. What shape is this? And a cone is nothing but a fancy three-dimensional what? So it's not a, sorry, you're right. It is a three-dimensional cone. That was a bad answer, or bad question. Good catch. It's a 3D triangle. Now, what kind of triangle? Because that matters. It's a 3D right triangle, isn't it? So here's what I want you to do for the bell ringer. The issue with this problem, and I'm just going to really highlight it in case it didn't catch, we don't want r in this problem. We don't want to have to deal with r anytime if we can avoid it. So the issue that we have is r and dr dt. That's the issue. Okay, we need a way to get rid of it. We want h. Why? How do I know I want h in this problem? We're trying to find how fast the height is changing, right? So I need h because I need dH dt. I have to have it. So we need a way to get rid of r and dr dt. Like, that's a problem. Now, the good news, back to our geometry problem, is you guys just correctly told me that cones are just three-dimensional triangles. Do you agree that this is what a cone kind of looks like if I do the two-dimensional version? Like, if I have this and then I spin it along this vertical, I would get my cone. Okay, just for the record, what we end the year with is awesome. I know it's not where we're at yet, but the very last thing that we teach, or that I teach in here rather, is how do we find the volume of something if we take this shape and then we spin it around an axis? Like, that's where this goes. And it's awesome because volume's a really hard thing to find if we don't have tools to do it. Anyway, not our focus yet. So check it out. From our picture, do I know anything about this? What's this top distance right here based on the picture from yesterday? 5 feet. What's this big distance right here? 12. Now, at some point, and I don't know when, the water fills up, right? I don't know what this is, but is this a radius at this point? I'm going to call this r, and that's when this height is what? It's when it's 5, right? Or h, and we'll do it when h is 5 later. Okay, do you guys agree that this is just a radius of the water in the cone, and this is the height of the cone, the water in the cone? Okay, here's my challenge for you, and this is technically your bell ringer. Using triangle similarity. My challenge for you, we wanted to get rid of r, right? That was the issue. Write the value for r, or an expression for r, in terms of h. Okay, so I'm going to give you guys a couple minutes while I do attendance, and you're going to collectively dig deep. I would encourage, we typically kind of separate by section here, which is an odd thing to see in a senior class, but that's okay. if your neighbors don't know, I would encourage you to stand up, walk, talk with somebody else. Like, amongst all of us, I think we have this geometry, and somebody might already have it done. Let's use our collective knowledge as a whole collective. I'm going to give you guys a second. We are going to use the fact that triangles of similar shape, or similar triangles rather, are proportional. Now I'm going to start with what Sean said. Sean said if we take the radius over 5, so r over 5, it should be equal to, what's the bigger triangles, r and h? Sorry, h and, gosh, I did it radius to radius, right? Now there's more ways we can do it. What else should I write here? H over 12, there. Sorry, it got weird there for a second. Is this the only way that we can do it? Can we do r over h? I'm going to put a question mark for now. If I do r over h, what should it be? 5 over 12. I can do it this way. I could also flip any of my ratios over. What I'm not allowed to do is I can't do r over 12. I can't mix and match here like this. So in either of these situations, we're going to get the exact same thing. Doesn't really matter to me which one we use. If we use this one, how would I solve it for r? So I would wind up with r equals 5h over 12. And what if I solve this one? Hey, it's still 5h over 12. Now, when I actually write this here in a second, this is how I prefer fractions like 90% of the time. But if I'm going to be differentiating stuff anyway, it's probably better to write this as 5/12 h. Okay, just so we see the constant multiple. All right, with this geometry stuff, does it ring a bell at least? Everybody remembers doing triangle similarity like this? And if you don't, do you understand what just happened? Okay, well, that's the part that I'm more concerned with. So let's see where our problem broke down and what we actually need to do. This thing gives us r's and dr's, and I don't want to deal with it. Okay, so I won't. Not yet anyway. Let's try this again. We're going to rewrite this volume, but I'm going to take out anything that's r because we have a way to write it. So check this. We're going to rewrite our volume, and I'm going to make really clear annotations. Rewrite the volume equation without r. Now, again, just because when we tried it the first time and it was a good thought, we couldn't plug in everything. So what that means is when we write our equation, we know that the volume instead is going to be 1/3 pi, and I'm just going to write this as pi thirds. It's a constant multiple. Again, if you didn't catch what I just did, on the first equation we had 1/3 pi. I'm going to write this as pi thirds. All I'm changing. Okay, times r squared, but what's r again? 5h, I'm going to switch color so that stands out. 5h over 12, because that was r. And what happened with that r in our original equation? Squared, and we multiply it still by, I heard 5 and I heard h. H. Why 5, just out of curiosity? I think I know, but I want you to make sure you can tell me. Mm-hmm. So, okay, I see that. I see what you're saying here. But we want to keep h. We don't want to change it to anything because we're cool with the HDT. That's what we're after. Okay, at this point, can we clean this up a little bit? And rather, help me clean this up a little bit. This becomes, if we do little steps, pi thirds times what? Can we all agree it's going to be 25h squared over 144? If I take this step, here's my 25 over 144, and I'm just looking ahead is all I'm doing. If I have h squared times h, can I just sneak into h cubed right here? I skipped one line where I just had the h squared in here, and then I just multiplied it through. Okay, at this point, there's a really ugly constant multiple, but we can deal with it. I'm not going to multiply it, but I am going to now do what? We have an equation that only has volume, or for volume that only has h. We noticed and I helped us notice, or you might have, that we had our equation and then we differentiated and it got us stuck. So here's our original equation again. What should we do with it? Let's differentiate it. I need to get a dH dt. This is just our second attempt. So let's do that. I'm going to take the derivative of both sides with respect to what? T, with time. Volume changes with time, and naturally that happens because the height of our column of water also changes over time. All right, I'll do the left. dV dt. Okay, that was easy. How about the right? What's the constant multiple going to be without having to multiply and get ugly numbers? And Bea, if you're tempted to use your calculator to 3 times 144, thought you were grabbing a calculator. I assumed wrong. My bad. Anybody object to me doing this? Because I don't really want to multiply it out yet. That's my constant multiple. And then I'm going to multiply this by the derivative of what? H cubed. So help me out here. What is the derivative of h cubed? 3h squared. And you said h prime, but I'm not going to write h prime. dh dt. Okay. Now, first thing. I jumped on Bea as soon as I saw her grabbing stuff because I thought she was getting a calculator. You may be tempted to multiply this out, right? Especially if you have a calculator. Can you see why I didn't? I could see that there was a 3h squared coming, and I knew that there was a 3 down here. Why would we multiply it out if we're just going to divide it anyway? I'm just going to cross them out here. Now, you would get the same thing even if you did multiply it, but I see that those are gone, which is pretty convenient. And we now have an expression that only has a dH dt. That's what we're trying to solve, right? So we're going to make a few notes here. We want, or solve for this is what we're going to do. And we'll just make a couple notes. You do not have to do this on every problem, but this is the first really ugly one. Do we know what this is? If you look back through your problem, how fast is the volume of water in our cone changing? I heard Angel whisper it confidently. 10 cubic feet per minute. We know that number. And we're trying to do this when, gosh, do we know what h is supposed to be? When h is, if we read back through the problem, 8? Okay. I need to find dH dt, and I know this, and I know this. It's just a matter of plugging and chugging at this point. Now, we are probably going to vary a little bit. I don't care either way. If you want to plug in right here and right now and then rearrange it to solve for dH dt, I'm good with that. Or if you'd rather rearrange it and solve for dH dt and then plug everything in, we're going to get the same answer, I think. I want you to plug in what we know, and I want you to solve for dH dt. Don't care which way you go. I want you guys to do the algebra part. We're done with the calculus. I just want to see if we can all carry through the algebra and get the same answer. Cool. If you're struggling and you go, Holly, I don't know how to do any of this algebra, I don't believe you, first of all. Like, I think that you might struggle, but you do know how to do it. But if you need a reminder, I'm here. Is plug in and then solve, or do you solve it for dH and then plug in? You plug in first? Okay, I'm fine with that. So let's do that. I'm just going to plug in, and I'm going to switch. I lied. I'm just going to keep everything purple. This is a 10. Now, I'm going to play the unit game like we did in physics. I'm not going to include the units on every step of the operation, but I will do it after the fact, just so I don't get this all gross and muddled as we're going. Okay, checking this out, I know that this is still 25 pi over 144. And then, is it a huge step if I say this is now a 64? Okay, and dH dt. Now, as I'm looking at these, there's a bunch of options. I don't have a calculator handy. I don't really want a calculator right this second. Realistically, we should have a calculator because if you give me an answer that doesn't, like, I'm okay with exact, but it depends on the context. Math class, exact pretty much all the time. But if you ever told me to cut a piece of wood at 5√2 inches, I'm going to tell you you're dumb and to shut up. Like, that's pretentious. There's a difference, right? Okay. So when I view this, and you don't have to view it the same way, but here's my head thinking. What goes into both of these? Because a 2 and I think a 4 will go into both of them. Anything bigger? Does 8 go into both of them? 8 times 18, I think, or 8 times 19 here. Whoa. 8 times 20 is 160, right? So this must be 18 since it's 16 less. So an 8 goes into that 18 times, and an 8 goes into this 8 times, and I've already simplified my fraction. There was something bigger that went into both. This, I'm going to simplify it one more step here along the way. What goes into 2 and 18? Dang it. What goes into 8 and 18? Every time. So a 4 and a 9? And somewhere, Leanne, I don't know what I did. I made a goofy mistake somewhere with the division as we were looking at it. I don't know what it was. Okay. Now, this is much nicer. And as we view this, well, let's just see if I clean up one little line of work, what do we have now? I get 10 equals, what's 25 pi times 4? One more time. 100 pi over, what's the only thing left in my denominator? 9, and we're still multiplying by dh dt. Now, only because I heard some erasing. I don't necessarily know, I have no idea why anybody would be erasing. Obviously, I'm not looking at your page. If it's because you're wrong, I would always encourage, don't erase. Mistakes happen. It's okay. Be aware of those mistakes. If you're erasing it because you did something different than me, doesn't mean you're wrong. Like, we can do math a bunch of different ways. I'm one step away from solving. What do you want me to divide by? Okay, so I'm not going to think about it like that. Can you give me an alternative way to view it? Because I don't want to think about dividing by a fraction. That's yuck. Yeah, or if I just multiply by the reciprocal is what I'm after. And I'm okay with 90 over 100 pi. It kind of bugs me that it's not simplified. How can I simplify it? Divide it by 10, 9 over 10 pi. Now, here's where we get to play the unit game. And we have to check, because this is a 1, we should do it to make sure our units are correct anyway. But 2, by checking our units, we're giving ourselves a second check of our math. If we talk about the height of water and time, how do we measure the height of water on our problem? It's in feet, and the time is in, is it seconds? It's minutes. So we're going to play the unit game with these right here, and we should wind up with feet per minute is what we're after. And I'm going to verify that's true. So with the units, just like we did in physics, if you want to include them like originally, you can, but I'm not going to do it until the very end. This was in cubic feet per minute. Okay, and let's see, this was a constant, or this was a constant, no unit on it. What is height measured in? Feet, and if we squared it, we got feet squared. So those are the only, whoa, not F to the T, feet squared. These were the only units in my problem, which means when I got to this point and I divided, this is the thing that really had the feet squared. I would have had feet cubed right here, divided per minute, divided by feet squared. That's what that would come out to be with my calculations. What happens with my feet? Yeah, you can say subtract, and I'm fine with that. If I do this, do we get the same thing? And what is the unit I'm left with? Feet per minute. What should I be left with? Is that how you talk about height changing? Yeah, so we're done. I have 2 things left to do. First thing is we put that label here. And now here's my challenge. Remember, we need to be specific. I'm going to give you guys 60 seconds. I want you to write a contextual sentence, and I'm going to help you pick apart and see, hopefully not, but why you're wrong. Cool. Write me a sentence explaining your answer in this problem. 60 seconds. Cool. The height of water, and these are the least fun thing that we're going to do. The height of water in the tank. When? When the depth is 8 feet, is, and here we go, is it increasing or decreasing? Increasing. Now, we're going to clean this up because we'll have to do a decreasing one as well. If it were decreasing, what would change about my answer? but I would never say it's decreasing at a negative rate. That doesn't make sense. The negative tells me that it's decreasing. Like that's the point of negative. So when we write our sentences, we're always going to use the absolute value. We'll just use the word increase or decrease depending on the context. The height of the water in the tank when the depth is 8 feet is increasing at a rate of, and what was that rate that we just found the height was changing at? 910 pyths feet per minute. And we're done. Okay. This is easily the longest problem that we have worked. For this, let's holistically take a little zoom out. And can you guys still read this, or is the writing too small at this point? I mean, you have your notes in front of you, so you can probably read yours also. So I will zoom back in just so if I point at stuff, you can see exactly what it is. Now, if we compare with our guidelines that we saw yesterday, the very first thing that we did was immediately we drew a picture. And in fact, I made you draw the picture. I forgot to print out our worksheets today. I got you. We'll figure it out. Okay. So here they are. We had that. What's the second thing of our guidelines say to do? All right. So here we picked out the given, and it wasn't explicitly stated, and this is going to be the hardest part. They're going to use the word filled, emptied, drained at a rate. Like you're going to see those keywords that show up that tell us that we have a rate of change given. So we found that, and we knew that is when H was 8, and we had that given on our picture here. And then we wrote an equation trying to relate all of our givens, right? Now, in this case, it happened to be like we didn't remember it, and that's okay. These things will typically be provided depending. But we wrote our equation, and then we tried to differentiate it. Immediately, we ran into trouble, so we saw that we had to fix something. So we fixed it, and then we did the same thing. We differentiated it once more. The most common mistake, if people can get these problems set up, like there's still times where there's issues. I'm going to make one last big comment, and then we'll probably do a little brain break so I can do a print of a worksheet for you guys. So the big comment, and this is regarding this problem. It's regarding pretty much every related rate problem that we're ever going to do. We only, and I'm going to underline that, we only plug in knowns after differentiating. Only then. We will only plug in our knowns after we differentiate. Okay. The most common mistake is that somebody will try to plug in their knowns and they'll just get a constant and they'll differentiate it and they'll say, oh, it's 0, which would make sense in that context. But remember, a lot of the time we're going to be given a dv dt or something with something with respect to time. We have to get the differential before the derivative, before we can do it. Okay, this problem is much harder than I was expecting us to do right away. Should we do a circle problem? Like 3-dimension stuff is naturally going to be harder. Real quickly, let me do some digging, and we can do a quick, let's see, wind up. So here's the next problem that we're going to work. You don't really need to know it's a rock dropped into a pool and that there's a ripple, but there is a ripple growing outward. Like waves push outward in a circle, and we saw that short video. I tell us how fast the radius is increasing, and we're told that we measure the centimeter or the radius to be some distance at this point in time. I'll give you guys a second. I'm going to cover that stuff. So for those of you that are watching this on a video, this is my lazy not writing it, and everybody else is writing it right now. We did just do a short Wine About It Wednesday, and the 3 biggest wines that we just came up with were portfolios, college applications, and the weather changing from beautiful to terrible as soon as school ends. And that I had to staple a bunch of packets. Mine seems so much smaller. Oh yeah, by the way, wag kanya magreklamo. Did you understand? Oh yeah, it's getting better. Getting better. I wrote it phonetically on the board here because I made somebody teach me the other day. I don't know if we've been through that in here or not. I don't really speak Filipino. Quit complaining, right? Quit whining, which is a perfect response after I just asked you guys to whine. All right, do we have this written? Almost. Okay, so I'm just going to do this so I can write it, or I'll just put it up on the board here in a second. Step 1 of related rates is to do what? We're going to draw a picture. Now, are we going to draw a beautiful, naturally spring-fed pond with pebbles dropping in cinematic fashion? No. I mean, you can, but I'm not going to wait for you to draw it, just so you know. For our example, check it out. Our rock drops into a pool. And what do the ripples look like? Here's my ripple. There it is. Cool. All right. Now, we know that the radius is growing. And if we want to label this a little bit more organized, we can do it like we did in physics, where we say, here's what we know. And you don't physically have to write this down. We do have a schema that we've used before to do problems like these, because this is like how every physics problem started. Okay, we have our picture, and let's just see if there's anything else I can add. The radius is increasing. We measure the radius to be 3 centimeters right now. So if I want to, I can say that, check it out, here's a radius, and I assume that I'm looking for when r is 3. So when r is 3, but I'm going to wait to put that until what I'm supposed to be finding. So I'm just going to call that the radius right now. Do we get a derivative given? Now that's a trick question. We do have a derivative given. Let me rephrase it. What is a derivative that we're given in these words? The radius. Why do we have the derivative for the radius? The radius is doing what? Is that changing? So there's a change in our radius. Okay. So how do I write that? How do we write the change of the radius? dr ys. And I don't normally stutter, so that was strange. I agree with you, but seconds is just a measure of time. dr dt. Okay, so anything else that we like? What is dr dt? 1 centimeter per second. Okay, now for this is a good practice. There's not a real natural spot to do this. What are all the variables that we have, though? And I'm just going to jot these down. I normally think this out, but on big, ugly problems, it might be helpful to do this like we did the last one. We have a radius that we're going to be working with. What else are we talking about? So, and I'm just going to count that as like, that's related to the variable r. What's the only other thing? Because we need to be able to write an equation to relate these things together, hence the related rates part. What are we worrying about changing? So we need an area as well. Now, whether you physically write this or not, like I want you to think this at least. What are we actually trying to find? I'm not trying to find the area. There we go. How fast does the area change? So that's the change in area over time, or dA dt. When what? When r equals 3 centimeters. This is our whole problem. We want to find dA dt when r is 3, and we happen to know this. So we have our identified stuff. Can we all agree that if I drop a rock in a ripple or in a pool, the ripples are going to do this? Like, they're not going to go the other way. That'd be crazy. Awesome and weird to see, but it's probably not going to happen. Okay, now here's the hardest part of these problems. And this problem is very different. It's much easier. Is there a way to relate radius of a circle and its area? So you say pi r squared. You did not give me an equation. And I know I'm being like nitpicky, but very intentional. The area of a circle is equal to pi r squared. And now I'm just going to start thinking it out. My next step would typically be to differentiate. Now, you don't have to be able to do the whole derivative in your head, but you probably can with this. And I'm just going to do as much as I can mentally. I'm going to get a dA dt. Is that okay? That's what I'm solving for. I'm also going to get an R or a dr dt. Is that okay? I know it, right? Cool. So I don't have to do anything different on this one. So what do? Yeah, let's differentiate it with respect to what? So here we go, d dt of these. And let's just do it. What's the derivative of a? dA dt. Okay, equals, what's the constant multiple here? Pi, and can you tell me why I left a little awkward space in front of it? What's the derivative of r squared? So 2r, r prime, or 2r dr dt. I'm going to put the 2 here. I'm going to put the r here in dr dt. Okay. At this point, we've done the exact same situation. Was this problem noticeably easier? For sure, but it's the exact same thing. We still found an equation. We said, let's differentiate it. We didn't have to do any weird substitution stuff, which was super convenient, but we did the same thing. Okay, we just want to plug in. Okay, we don't even have to rearrange, right? Because I'm trying to find dA dt, and it's already here. I'm trying to find dA dt when, what do we know? When r is 3, so it's 2 pi times 3. And what was dr dt? 1. Now I'm going to do one little thing here. I'm going to play the unit game right now because I'm already here. This r was measured in what? That was centimeters. And this 1 was measured in what? What is my unit going to be in the end? And centimeters squared per second, does that sound like an area over time? For sure. And I think we can even get the answer here. dA dt, based on what we have written on the board, is how many centimeters squared per second? 6 pi of them. Are we done? We're done with the calculus of it, for sure. I want you guys to write me a sentence knowing that 6 pi was the answer. I'm going to go ahead and scroll up in case you didn't write word for word everything that you needed. And that's a me problem more than a you problem. Do you need me to scroll back down, Mickey, as well? Hey, I got 6 pi as well. That's a good sign. Good. Cool. I want you to write me your contextual sentence. It can be lazy as long as you don't use the word it. Abigail, I saw you just put a dot on your page. What's your sentence? Love it. The area of the ripple or the circle, whatever you want to word it as, just not it. The area of the ripple is increasing at 6 pi centimeters squared per second when the radius is 3 centimeters. Okay, just a nice question for you. If I checked it again and I didn't do the problem, but if I tried to do it at 4 centimeters, is the area going to be changing faster or slower? Faster, because check it out, even though the radius just changes at the same speed all the time, we get way bigger with the area, right? In fact, it's going to be proportional to the square of the radius is what's going to ultimately happen, which is way faster. The bigger the circle, the more area that you add for every little bit you add. Okay, these problems, very similar in nature and just approach. This probably did not make you feel bad. I don't think. This is the same idea. The first one was hard, and that's okay. Hard problems aren't bad unless you just decide to give up and not try. Tomorrow in class, I will give you guys this wonderful thing, and we'll work a couple together, but it's essentially a work day. Sweet. I really debated giving you homework, decided against it. So make of that what you will. Yes. Did you do your reflections? Okay, finish them. Did I give you your practice test? Okay. I will. I have not. I'll get it done. I'll try to get it done at lunch. I have a meeting today. I can't get on my computer at home, and it really messes with my ability to